Okay, so this is number 14, section 6.3. Now I will. Okay, yeah, sorry, because I re recorded this, so it's gonna sound kind of spotty. So, the national average SAT score for verbal and math is 1028. Suppose that nothing is known about the shape of the distribution and that the standard deviation is 100. Okay, well, they told us that the national average is 1028, so this means it's our mu. The reason I say that is because they did not say, like, oh, this is a sample and the mean of this sample is the 1028. It's just in general mean, so it has to be the population mean. Similarly, it's gonna be the sigma for the standard deviation because it's a population standard deviation rather than that of a sample. So now they said that if a random sample of 200 of scores were selected and the sample mean were 1050, would you be surprised? Okay, well, 200, right? So my sample size is 200 and my x is gonna be 1050. So now let's just get something clear. Because I have x bar rather than just any data value x, that means that I'm not really looking at a distribution of the data. I'm looking at a distribution of sample means. Okay, so what does that really tell me? So what that's telling me is that rather than it having a lot of variance and looking like a bell-shaped curve in case it's normal, it's gonna look something a lot weirder where it's not gonna be as variable. Actually, it's gonna look something like this. Now, why, you might ask? And that's because if we're trying, like, let's try to find the z-score. When we try to find the z-score of a problem like this, it's usually gonna be z equals x bar minus mu divided by the standard error of the mean. Rather, we're not dividing by just the standard deviation, we're dividing by the standard error of the mean. So it's going to be sigma divided by the square root of n. This is really significant because it's due to this that our variance is not that big. When we have a nice bell-shaped curve, when we have data that's really nice and like bell-shaped curve, like really nicely distributed across the curve, we have quite some variance. But when you divide your standard deviation, by the square root of n, this whole thing decreases, thus increasing this. And if your denominator is smaller than your numerator, then your z is gonna get bigger. Right? Because if you have a big number on top, like 4 over 3, this is going to give you 1.333. It's going to be a lot bigger than if you have 3 over 4, which is 0.75. But this is just an example. But this is what happens. When you have a distribution of sample means, it's not as nice and neat as a regular data distribution. It's kind of like, it goes up really fast, comes down. It's very concentrated in one area is what I'm trying to say. There is no variance. Well, there is some variance, but it's not as big. And actually, a nice thing about it, or I don't know if it's like that nice, but as the sample size increase, the standard deviation as the n really gets a lot bigger. Like right now we have 200, which is quite big. As this gets bigger, this whole fraction gets a lot smaller. And because this fraction gets really small, then z will be considerably big. So let's look at the data. We have a standard deviation of 100 and a mu of 200. My x bar is 1050. If I assume that this was my x, then then 1050 is not really that different than 1028, because look at it, the standard deviation is 100. So that means if I had like something like this, this is my data. Let's just say this is a data distribution, and this is my 1028. My 1050 would be somewhere around here, 1050. But that's not going to be the case. And to prove it, we're just going to have to calculate the z is equal to x minus mu over the standard deviation divided by n, which is gonna be my x bar is just gonna be 1050 minus 1028 over 100 divided by the square root of 200, and this is gonna give me 3.11. So like let's consider this as 0 and say this is like a z-score distribution of sample means. 3 is really, really small. It's gonna be 3.11 right here. And if we go to a z-score table to see how small it is, whereas it's 3, we said it was 3.11, yeah. So sorry, there's a lot of writing. The 3.11, it's gonna be 3.1. This is 3.10, this is 3.11 right here. So it's gonna be 3 9s and a 1. So basically the probability that I have anything smaller than that, like all this area right here, this is 0.9991. So the probability of me getting anything bigger is really, really small. It's gonna be 1 minus 0.9991. The reason I said 1 minus is because, again, it's still a probability distribution, and any probability distribution, no matter how it looks like, has to be 1. So it's gonna be 1 minus this probability, the probability that it's less than, to get the probability that's greater than. So I'm gonna get 0.0009. And see how small a probability that is? Basically, if I want to do it as a percent, this is 0.09% chance that I'm ever gonna get something higher, like a mean that is higher. Especially since n is so big, it would be really surprising if with such a big n, I'm gonna get such a large mean. So yeah, because as n gets bigger, you're supposed to be very, very close to the population mean rather than any other number. But because even such a small, it looks like it's a small variation, but it's actually not, because it's a sample mean rather than a data, because it's a sample mean rather than a data value. If it was a data value, if it was just like one person who just happened, because that's what data values stand for, they just stand for one person. If it's just like, okay, like one person, he scored higher than the average, good for him. But if it's 200 people and their average is higher than the population average, then that's pretty rare. It's really, really unlikely to happen. So I would be very, because the question here asks you if it would be surprising to have a mean of 1050. I think it would be very surprising to have a mean that far away from the population mean, because even when you take a sample size that's 30, because it becomes normally distributed, and then the mean, because if we're doing a data distribution and you have a sample size that's bigger than 30, then it becomes the data becomes normally distributed with a mean kind of close to the population mean. But here it's really, really far away, and because it's far away with respect to means. Like you're not supposed to have a sample size that big and get a mean that is this far away from the population mean. But yeah, thank you for listening.